Well, it's a real pleasure to be here and to have a chance just to meet with you and talk about some of the problems that we're facing. Now, some of these problems are local, some are national, some are global, but they're all tied together. They're tied together with arithmetic, and the arithmetic isn't very difficult. And what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary, steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year, because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another. In the summer of 1986, the news reports indicated that the world population had reached the number 5 billion people, growing at the rate of 1.7% per year. Well, your reaction to 1.7 might be to say, that's so small. Nothing bad could ever happen at 1.7% per year. So you calculate the doubling time, you find it's only 41 years. More recently, in 1999, we read that the world population had increased from 5 billion to 6 billion people. The good news is that the growth rate had dropped from 1.7% per year to 1.3% per year. The bad news is that in spite of the drop in the growth rate, the world population today is increasing by something over 80 million people every year. Now, if this modest current 1.3% per year could continue, the world population would grow to a density of 1 person per square meter on the dry land surface of the earth in just 780 years, and the mass of people would equal the mass of the earth in just 2,400 years. Now, we can smile at those. We know they couldn't happen. This one makes for a cute cartoon. The caption says, "Excuse me, sir, but I am prepared to make you a rather attractive offer for your square." Now, there's a very profound lesson in that cartoon. The lesson is that zero population growth is going to happen. Now, we can debate whether we like zero population growth or don't like it. It's going to happen, whether we debate it or not, whether we like it or not. It's absolutely certain people could not live at that density on the dry land surface of the earth. Therefore, today's high birth rates will drop. Today's low death rates will rise till they have exactly the same numerical value. That will certainly be in a time short compared to 780 years. Now, you don't need any more arithmetic than this to evaluate the absolutely contradictory statements we've all heard and read from experts who tell us in one breath we can go on increasing our rates of consumption of fossil fuels. In the next breath they say, but don't worry, we'll always be able to make the discoveries of new resources that we need to meet the requirements of that growth. Well, some years ago in Washington, our Energy Secretary observed that in the energy crisis, we have a classic case of exponential growth against a finite source. So let's look at some of these finite sources. From the work of the late Dr. M. King Hubbert, we have here his semi-logarithmic plot of world oil production. The line's been approximately straight for over 100 years, clear up here to the year 1970. Average growth rate, very close to 7% per year. So it's logical to ask, well, how much longer could that 7% continue? Well, that's answered by the numbers in this table. In the top line, the numbers tell us that in the year 1973, world oil production was 20 billion barrels. The total production in all of history, including that 20, was 300 billion. The remaining reserves, 1,700 billion. Now, those are data. The rest of this table is just calculated out. Assume that the historic 7% growth continued steadily each year following 1973, exactly as it had been for the preceding 100 years. Now, in fact, the growth stopped. Not because of the arithmetic, it stopped because OPEC raised their oil prices. So we're asking, what if? Suppose the growth had continued. Let's go back to the year 1981. By 1981, on the 7% curve, the total usage in all of history would add up to 500 billion barrels, the remaining reserves 1,500 billion. The reserves at that point are 3 times the total of all that have been used in all of history. That's an enormous reserve. Well, we know for 7% growth, the doubling time is 10 years. We go from 1981 to 1991. By 1991, on the 7% curve, the total usage in all of history would add up to 1,000 billion barrels. There'd be 1,000 billion left. At that point, the remaining oil would be equal in quantity to the total of all that we had used in something like 130 years of the oil industry on this earth. By most measures, you'd say that is an enormous remaining reserve. We go one more decade to the turn of the century, that's like right now. That's when 7% would finish using up the oil reserves of the earth. Well, it's interesting to read what the experts say. Here's an interview in Time magazine with one of the most widely quoted oil experts in all of Texas. They ask him, but haven't many of our bigger fields been drilled nearly dry? He responds saying there's still as much oil to be found in the U.S. as has ever been produced. Several things this guy's written. I don't think he has any understanding of this very simple arithmetic. Well, in the crisis back in the 70s, ads such as this appeared. This is from the American Electric Power Company. It was a bit reassuring, sort of saying, now don't worry too much, because we're sitting on half of the world's known supply of coal, enough for over 500 years. Now, where did that 500-year figure come from? Well, it may have had its origin in this report to the Committee on Interior and Insular Affairs of the United States Senate, because in that report we find this sentence. At current levels of output and recovery, these American coal reserves can be expected to last more than 500 years. There is one of the most dangerous statements in the literature. It's dangerous because it's true. But it isn't the truth that makes it dangerous. The danger lies in the fact that people take the sentence apart. They just say coal will last 500 years. They forget the caveat with which the sentence started. And what were those opening words? At current levels. Now, what does that mean? It means if and only if we maintain zero growth of coal production in this country. So let's look at a few numbers. We go to the annual energy review published by the U.S. Department of Energy. They give this figure as the coal demonstrated reserve base, and it carries a footnote that says about half the demonstrated reserve base is estimated to be recoverable. You cannot recover and use 100% of the coal that's in the ground. So this number is half of this number, and we'll come back to those in just a moment. Now, the report also tells us that in the year 1971, we were mining coal in this country at this rate. 20 years later, 1991, we were mining at this rate. Put those numbers together, and the average growth rate of coal production in those 20 years was 2.86% per year. And so we have to ask, well, how long could a resource last if you had steady growth in the rate of consumption till the last bit of it was used? Well, I'll just show you that equation. For the expiration time, I'll tell you It takes first-year college calculus to derive that equation, so it can't be very difficult. You know, I have the feeling there must be dozens of people in this country who have had first-year college calculus. But let me suggest I think that equation's probably the best-kept scientific secret of the century. Now let me show you why. If you use that equation to calculate the life expectancy of the reserve base, or of the 1/2 the reserve base that's estimated to be recoverable, for different steady rates of growth, you find if the growth rate is 0, the small estimate would go about 240 years. The large one would go close to 500 years. So that report to the Congress was correct. But look what we get when we plug in steady growth. Back in the 1970s, we had national goal of achieving 8% per year growth rate in coal production in the United States. If that could be achieved and continued, coal would last between 37 and 46 years. President Carter cut that goal roughly in half, hoping to reach 4% per year. If that could continue, coal would last between 59 and 75 years. Here's that 2.86 that we just saw, the average for a recent 20-year period. If that could continue, coal would run out between 72 and 94 years. That's within the life expectancy of children born today. The only way we're going to get anywhere near this widely quoted 500-year figure is to do simultaneously two highly improbable things. Number one, we've got to figure out how to use 100% of the coal that's in the ground. Number two, we've got to figure out how to have 500 years of zero growth of coal production. Let's now go back and note that in the 1970s there was great national concern about energy, but this concern disappeared in the 80s. Now, the concerns about energy in the 70s prompted experts, journalists, and scientists to assure the American people that there was no reason to be concerned. So let's go back now and look at some of those assurances from the 70s so we can see what to expect as the energy crisis returns. Here is the director of the Energy Division of the Oak Ridge National Laboratories. He's telling us how expensive it is to import oil, telling us we must have big increases in our use of coal. Under these conditions, he estimates America's coal reserves are so huge they could last a minimum of 300 years, probably a maximum of 1,000 years. Now, you've just seen the facts. Now you see what an expert tells us, and what can you conclude? There was a 3-hour television special on CBS on energy. The reporter said by the lowest estimate, we have enough coal for 200 years, but the highest enough for more than 1,000 years. You've just seen the facts. Now you see what a journalist tells us after careful study. And what can you conclude? In the Journal of Chemical Education, on the page for high school chemistry teachers, an article written by the scientific staff of the journal, we read that our proved coal reserves are enormous, and they give a figure. These could satisfy present U.S. energy needs for nearly 1,000 years. Let's do long division. You take the coal they say is there, divide by what was then the current rate of consumption, and you get 180 years. Now, they didn't say current rate of consumption. They said present U.S. energy needs. Coal today supplies about 1/5, around 20% of the energy that we use in this country. So if you'd like to calculate how long this quantity of coal could satisfy present U.S. energy needs, you have to multiply this denominator by 5. When you do that, you get 36 years. They said nearly 1,000 years. Newsweek magazine, in a cover story on energy, said at present rates of consumption, we have enough coal for 666.5 years. And the 0.5 means they think it'll run out in July instead of January. Now, if you round that off and say roughly 600 years, 600 is close enough to 500 to lie within the uncertainty of our knowledge of the size of the resource. So with that observation, that is a correct statement. At present rates, meaning zero growth, we have enough coal for around 600 years. The whole point of the story that this led into was that we have to have rapid growth in coal consumption in the United States. Now, it's obvious, isn't it? If you have the growth they're writing about, it won't last as long as they said it would last with zero growth. They never mentioned this. I wrote them a long letter, told them I thought this was a serious misrepresentation, to give the readers the feeling that we can have all the growth that they're writing about and still have coal around for 650 years. I got back a nice form letter. It had nothing to do with what I'd tried to explain to them. I gave